Good afternoon and welcome to Design Master Training. My name is David Robison. Today we are going to be looking at creating and modifying families in Design Master Electrical RT. If you're attending the training live, you can ask questions in the chat box. If you're watching the recording of the training, you can call or email with questions. Our phone number is 866-516-9497. And our email address is support@designmaster.biz. So let's get started looking at modifying families in Design Master Electrical RT. I'm going to take a look at our project here. We've got, this is the Revit sample project, and we've got this cooling tower here. So when families are created, our software will do as much as it can with them. But there's certain information that Revit doesn't have that you need to provide through our interface. So if I run the instance edit command, you can see that this is being seen as just a branch circuit device. It's just a generic device connected to a panel. And we've pulled some information like the load from the Revit model. But a lot of the stuff like the FLA, MCA, MOCP, we can't pull from the model because Revit doesn't have ways to specify that. Now you can use the instance edit and modify it on an individual basis for each item, but we also have the ability to modify the families so that when you put your pieces into your model, they have all this information specified. So I'm going to cancel out of this. I'm going to run the Revit edit family command. This will pull up the family in Revit. And now if you go to the DM electrical ribbon, you'll see that we've got a new option here, the family edit command. So if we run that, you will see that it pulls up the family edit command, and we now have the ability to make changes to this family, which will then be seen when it's used in the project. So we have two basic types of devices that we work with in our software. We have what we call a branch circuit device, what we call distribution equipment. The electrical industry doesn't have necessarily standardized names for these things, but this is how we view them in your model. Distribution equipment is panels, transformers, pretty much anything that's connected to, has other things connected to it is a distribution equipment. And then branch circuit devices are the things at the very end of your model that are actually have the electrical loads on them. So be that motors or elevators or receptacles or light fixtures. So this is a piece of mechanical equipment, so it would be a branch circuit device. And we have two options. We have the other, we also have the equipment connection. So when it's set to other, equipment connection has a couple more options. Other is pretty much everything else. As we expand our software, we might have more options there, but right now it's just the two. And so other is just kind of generic stuff connected to a circuit. And you really have one option to specify, and that's the circuit description. So we can specify a value here, and then when this device is circuited in Revit, it will actually pick this up and fill it in to the circuit for you. So it pulls in by default the family name, which in this instance is really long. So we're going to overwrite that, and we'll call this cooling tower. So now this is the circuit description for that family. And then we can load this back into our project. Overwrite our settings there. And if I take this piece of equipment and I pull up our circuit edit, it'll, if you have a piece of equipment selected and do circuit edit, it'll pull you to the circuit that is connected to automatically. And so the description here is set to cooling tower. That's being pulled from that family. So if we recircuit this to a different circuit, that cooling tower description will be removed from this circuit and pulled to the other circuit for you. If we change it in the family, it'll be changed here. So we are controlling the description through the family definition. You also have the ability at the instance level to override that. So we could say, hey, this is a cooling tower, but I want to actually call this CT1 in this project. If we do that, the instance setting is going to override that family setting. And then we go look at the circuit, and now it has that description being pulled from the instance instead of from the family. going to reset that to use the family setting. And we'll go back and take a look at a couple more settings we can change in the family. We pull up the family again, run the family edit command. Now let's change this to an equipment connection, and we get a couple more options. So we still have the circuit description choice, but it adds the rest of this information down here. First, we have the option to show it on the OneLine diagram, so you can show pieces of branch circuit devices on your OneLine diagram. By default, they don't show up because most stuff you don't want on your OneLine, just the bigger stuff. But you can change that to be yes, and then when you generate your OneLine, it'll show up automatically. You can also specify the FLA, MCA, and MOCP values. These you get from the cut sheet from the manufacturer typically. And so you can use specify that information here, and then we'll use it for sizing both the breaker and the wire size. We also have the motor multiplier and the motor XR ratio. These are used for fault current calculations. So if it is a motor, we feed the motor load back into the system if there's a fault and calculate the fault from the motor. By default, the multiplier for that fault is 4 times the motor load, and the XR ratio is set to 5. For most commercial equipment, those values are just fine, and you don't need to mess with them. But if you have a piece of equipment that has different values that you know, that you want to model a little more precisely, you do have the ability to come in here and adjust that. So standard commercial buildings, what we, for the most part, are focusing our software on, these are good enough defaults, and you're not going to have anything better typically. But if you're in the more industrial world or have some specifically large motors that you want to get modeled properly, you do have the ability to override those. We're going to ignore those for the moment, but we are going to take a look at these other values. So if I cancel out of this for a moment, I'm going to go back to my project. If we look at this circuit where this item is connected, we currently have a 70 amp breaker, 70 amp circuit is connected to it. So we're going to then go back to the family and run the family edit command. And now I'm going to set an MCA of 40 amps and MOCP of 100 amps. Then we can specify how we're going to size the breaker and the wire. I'm going to set the breaker to size based upon the MOCP, and I'm going to set the wire to size based upon the MCA. We make those changes. So now we're going to use these values. We're telling the software to use those values to size it. Click OK. Load that back into our project. So we got that new definition in there. And now when I run the circuit edit and take a look at this circuit that this is connected to, you'll see that it's going to pull in that breaker size. We have a 100 amp breaker based on the MOCP setting we chose, and it now has a 40 amp wire. So it's got the number 8s rather than whatever it had before for the 70 amp wire. So you can, at the family level, define certain families to have their MCA, MOCP values and breaker and wire sizing. And then every time you use that in your project and in future projects, it'll have it set automatically. And if you don't want to do that, or you need to override it, you always have the instance edit, and this is where you can come in and make changes. So you could say, okay, I'm going to size this, I'm going to set it to size based on MOCP and MCA, but maybe I set those individually because I have one model that's used for a lot of different types of equipment. So you could leave the sizing as the family default and then override this MCA, go from 40, we'll say, well, maybe this is actually a 50 amp load, and the MOCP for this one's actually 90. So we can make those changes and override what the family values are. And then when we run the circuit edit, it will use that. We'll get the 90 amp breaker and the 50 amp wire. Those are the settings we have for branch circuit devices. We can also make changes to distribution equipment. So let me pull up my distribution equipment plan here. So again, distribution equipment are panels, transformers, anything that connects to something else that has something downstream of it being powered that has other things connected to it. is generically how we think of distribution equipment. So when you run the edit panel command, we have on the right-hand side all the information that we need about those panels and transformers. And some of this stuff we can override in the family. So if we go take a look at the family edit, I'm looking at a transformer right now, so we'll look at transformer settings. So we run the family edit. It's by default just, it kind of comes up as a branch circuit device. We can override that to distribution equipment. If we choose other, there's just a few choices. And this is for something that's basically not a transformer and not a panel. So you have the ability, we can add additional information to the description that's in the upstream circuit. So we will transfer by default the panel or the device name. You can also put a prefix. You could say panel such and such, and you can have a suffix if you want to have information after the panel name transferred up to the circuit. You can also specify a default neutral and ground size. And for the neutral, mostly we can do same as phase, and then there are cases where you want a double neutral. This is where you can say this type of panel or transformer always has a double neutral. And then the ground, we size it automatically, or you could choose which table you want to size the ground to this item automatically. You can also do custom and specify just a specific ground size and its specific neutral size as well. For transformer, we then add a couple additional pieces of information. You can specify the size of the transformer. Revit doesn't have an intrinsic transformer KVA value, so everyone has their own, including our software. So this is where you can, in the family, set it so that when you put in what you have modeled as a 100 kVA transformer, it'll come in knowing that's what size it is. You can specify whether it has a K-factor rating, which is used for scheduling purposes. And then you can also specify the impedance and the XR ratio, which do feed back into the fault and voltage drop calculations. So we have a default impedance that we pull based upon the size of the transformer. It's kind of got some generic values in there, and you can override those as appropriate. And then the XR ratio, again, you can override. We have a default of 5. Most commercial buildings, that's going to be correct and acceptable. But if you have a situation where you want to be more precise for that calculation, you can set it there. Now, all of this information up here is for every instance of that family. You also have the different types that you can choose. And so down here, you can override or set the values for each specific type. And this is a good example of where you would want to do that, because we have the specific types defined with the different sizes. So we'd actually want to set the KVA differently for each of these. So you want to come down here, say, okay, I'm going to override these family values. And this one isn't a 100 kVA transformer. It's actually a 15 kVA transformer. And do the same thing with the 30 kVA transformer and so on. As you can tell, it's a little bit of work. So there's definitely some front-end work you have to do to get things set up. But then you can reuse your families, and it's got all this set up ahead of time. So you could go through there and continue setting your sizes, your KVA sizes, or whatever else you need for those transformers. If I go back to our model, if I click on the transformer, it is a 500 kVA, so let's specify the 500 kVA type properly at least. Run the family edit command. Going to scroll over to the 500 section. We'll set it to a 500 kVA. And just to see where it's being set, we'll set the K rating to K40. And we can also adjust the impedance. It gives us a 2.5. We'll set that to 2. Click OK. Load all of those into the project. And now when we run the panel edit command on that transformer, you'll see that the transformer KVA is set at 500. In fact, it's fixed. So if we go to a different transformer that's not been specified this way, we can change that KVA because it hasn't been set in the family. If you set your KVA in the family, we assume that that is kind of at that point an intrinsic property of that transformer, and you don't actually want to be able to override it anymore. So it fixes it at 500. It fixes the K-factor rating at K40. with the idea being that if you wanted those different, you would need to have a different choice in your family to set that to. We also have the transformer impedance and XR ratios, again, fixed based upon the setting from the family. And again, if you want to have them different, that you would want to choose a different family modeled differently. And if you do want to be able to set those uniquely for each instance, then you don't want to modify the families. So it's a question of how you want your workflow to work as to whether you want to set these in the family. But if you do set them in the family, they will be pulled in here and they'll be displayed. So if we change this from that 500 to say the 15, horribly undersized, but just for, and it's actually going to disconnect it because nothing works anymore. If we do that, you'll see that now we have the 15 amp kVA transformer, and it has the difference impedance, and XR is still 5, but it's there. So those are the settings we have for transformers. And then we have also settings for panels. So we'll take this panel here, run the edit family on it, run the Design Master family edit command, change it to a panel. And for panels, we have these choices. We have the bus size in amps, so you can specify that. We have the disconnect type, whether it's main lugs only, a main breaker, or a fused switch. So if it's main lugs only, the trip and the frame aren't set because those are not, it's main lugs only. If you set it to a breaker, then you can actually set the disconnect trip and the frame size. They default to match the bus size, but you can override them as appropriate. And then again, same as the transformer, you can set those for each type in the family. And so this is an example of where you'd want to do that and say, okay, this is the 100 amp, and then this is the 125 amp bus panel. So you can override the bus, but then you can leave the same, leave the other settings just based upon the family. So we can say, okay, this is actually a main breaker, disconnect trip and frame are based on the bus size, and then set the bus size based upon each type. Set that to yes and 250 and so on. Let's take a look at our panel here again to see what sizes are being used. So that is 100 amps right now. So let's make sure we at least get the 100 amp setting right. So we have 100, the 125, the 250 are all set. So we can use those now. I will load that into the project. So now the main, the bus amps is being pulled from the family. Again, it's fixed at 100, you can't change that. So the idea is that the bus size of the panel is intrinsic to it, and if you wanted a different bus size, you would need to choose a different family type. The disconnect type and the disconnect size can be changed because you can actually swap out a breaker in the panel pretty easily. So that is something that we want to be able to override for each panel. So we'll, by default, have it match the bus size, but you can override it if you want to. If you're actually putting in a smaller breaker, you could say, okay, this is actually an 80 amp trip, even though it's a 100 amp panel. We're not actually going to use as big a breaker as we could put in there. So you can do that. We're not able to use the Revit values for these. Revit also has a disconnect type and a disconnect size in there, but they're actually exactly backward in terms of how they're specified. In terms of, I think the trip is, the main disconnect trip is a family value that's intrinsic to the family, and then the bus size can be changed on an instance, which is exactly opposite of how it should be. So we were not able to salvage that feature from Revit, and we replaced it with our own. So we're using our own values there. So those values are setting the bus size and the disconnect sizes. All of that information does feed then into the OneLine. It can show up as shared parameters in the schedules, and then in the OneLine diagram that we export, that shows up and it actually changes the graphic. So if you change your disconnect type, your panel draws a little differently, whether it includes a breaker or not, or a fused switch. Those are the options that we have available for modifying families. That's what you can do with our software. to predefine your values to make working on your future projects a little bit more easy. So it's a little bit of setup time ahead of time, but the hope is that you get the payback on future projects in terms of quality control and just ease of loading the values. Yeah, the basic idea with our Revit software is that Revit, it does certain things, but then it just kind of stops. And some things it tries to do doesn't do very well, and then other things it doesn't even attempt. So we try to come in and make it a little more useful. We started with the idea that feeder sizes in Revit are wrong, basically. And so no one that we have run into yet says that they actually use the feeder sizes in Revit. And if you don't have a feeder size, you can't do anything. So we took out their feeder sizing, put in our own, and then once you have feeder sizing, you can do fun stuff like voltage drop, and fault calcs, and arc flash calculations. And then we also said, hey, we've got this one-line diagram in Revit or AutoCAD. We should be able to do something in Revit. So we do a one-line diagram based upon your Revit model as well. So if I pull up this voltage drop schedule, it's a standard Revit schedule, nothing special here. We're just using shared parameters that we've defined in our software, but the schedule is a standard schedule, so you can modify it and publish it like you would any other schedule. When I run the calculate, our software calculates the voltage drop at each point. We've got the 3.2% voltage drop here on EP2. So if we take this panel upstream, we run the panel edit. And so here, as I was saying, there's, Revit has some information, but there's other information it just doesn't have. So this is where we specify the information that Revit is lacking. Some of it you can specify in the family, and then some you specify, in each instance. This should look very similar to what we do in AutoCAD. It's arranged a little differently, but the set of values we can specify is pretty much stolen from our other software because that software works well. So this PP2B, we can come down to the feeder settings, which exactly match what we have in AutoCAD. It's a 300 amp panel, so it's a 300 amp feeder. We can upsize it to a 400 amp feeder. And then we redo the calculation, and it'll update the voltage drop values. The feeder length we pull from Revit. So based upon where the devices are located, we calculate a distance either at right angles. We can also do a straight line distance. Revit has ability to draw out a circuit path. If you've done that, we can use that value. And finally, you can use a fixed where you just type it in and tell us what the feeder length is. So those are the options we have for the feeder length, exactly the same as what we have in our AutoCAD software. Revit, if you don't do the Revit calculated length, if you just let Revit guess, it gives you a value between a straight line and a right angle distance. I don't actually know how they do their calculation because it's not anything that we're able to match. So we don't use their one unless you do the Revit path. So that's what we have for the feeder sizing. We also do fault calculations in Revit. So if I come here to this panel and set the transformer and set a starting fault, and this is still a 15 kVA panel or transformer, which is going to be way too small. I'm going to bump that up back to the 500 kVA. Go back to our schedule and run the calculate, and it'll update the fault values for you. So the basic value proposition of the software is that you've got this model in Revit, rather than redoing it in Excel or SKM or EasyPower to get your fault values and your voltage drop, why don't we just actually use BIM for what we have been promised that it could do and have a single model where we pull all these values out of. Then we can also do a one-line diagram. Now the drafting for that is done in AutoCAD. So it can generate it for you. It'll kind of do a first pass layout. We know it's never quite right, so you have to go back and make your changes in terms of just laying it out so it looks nice. Pull this transformer down so that label isn't running into there. Maybe we've got some additional notes we want to put in here. We can pull this whole section down. And then we come back here and say, this is a 400 amp switchboard. Maybe it needs to be an 800 amp switchboard. We go into Revit, run the panel edit command, take that switchboard, bump it up to 800 amps, maybe give it a full name, make whatever changes you have, run the export command, so push all that information back out, and then over in AutoCAD, we're going to run the update and it'll pull that in. Now we've also moved this panel here, moved this panel over here. We don't want to lose that. So all that's going to stay. It's just going to update the information with those new changes that we have. So we run the update command. It pulls in the new information and it'll give us the 800 amp panel, 800 amp feeder, new label. But again, all of this other information stayed. And then you link this back into Revit for publishing purposes, typically. All of these graphics, everything in here is totally customizable because no one's one-line diagrams ever look the same. So this is just kind of an example, representative graphics, but we can adjust these out of the box. We have some different choices that you can use, and then you can override it with your own. So if we want to do just a transformer with a ground, we can do something like that. If we want to move the labels around, we can do that. If we want to add different labels, we've got a bunch of different labels depending on what you like to put on your one-line diagram. Maybe you want to specify your fault. You can do something like that. And also a bunch of options for once you've got something looking good, we can say, hey, I want this panel label to be matched by these other ones. And it'll copy that over to those other ones. The final big feature that we have, or set of features, is the branch circuit sizing in Revit. When Revit does its branch circuit sizing, you basically get 20 amp circuits everywhere. Our software overwrites that and actually attempts to size the circuits for you. And that's the overview of our software. At this point, I'm taking any questions that people have. So if there's anything you'd like to see, anything you'd like to chat about, this is your chance to do that. Oh, there's a question. How do you show an ATS? So step one, model an ATS properly in Revit. And then once you have that done, everything just works in Design Master exactly as you would like it to. Modeling an ATS in Revit is quite tricky. Because it requires really understanding exactly how Revit works. For fun, we can try and do it. I'm not a Revit expert, and I'm going to fumble and stumble through this, but we can see if we can make it work. So step one is we need a transfer switch family. And if I go into Systems, and I put in electrical equipment, I'm going to do load family, and I have all my default Revit families. I think they actually have one that they claim, at least, is a transfer switch. There we go, automatic transfer switch. We will put that in, throw it down here so that we have one. Now if I go edit this family, all right, so they have an automatic transfer switch. It's really poorly defined because it has a single connection. And so if you use this transfer switch out of the box, you're like, how does this work? It doesn't do anything. And the answer is that you need a second connection point, again, properly defined in order for this to work. Let's see if we can make that happen. I'm going to create. We'll try and make an electrical connector. I'm going to connect it to a face. We'll throw it over here. There it is. So I have a new electrical connector here, and I'm going to make all my settings match the other one. So it's a three pole 480 volt. I think that's pulling those from various things in the family. I'm just going to type them in and be lazy about it. Everything else is being pulled, kind of default values. Power factor's not going to matter. Okay. Now we have a second connection. Load this into the project, overwrite the existing version. Now we have this transfer switch. It has two connections. Now the question is, can we get it connected to two different things? We'll see if we can pull that off. See, this is where I run into trouble, because for whatever reason, it doesn't want to connect it to anything. There's magic you have to do in order to get it to work properly. All right, I have another transfer switch that maybe will work better. Now this one, I can power connector 1, and we'll do LP2. And cross our fingers, power. No, see, it's already connected. All right, let's see if we can figure this out. I think I've got two systems both connected to LP2. I'll take the second one. If we connect this to LP3. Okay, I think I've actually got it connected to two things now. Then we go into DM Electrical, run panel edit. So here's the new transfer switch we created. So it is connected to LP2. And you will notice it's listed here a second time, connected to LP3. So LP2, and we list the circuit LP3, and then it also says feeder 2. So if you get it all modeled properly in Revit, and you can connect it to two sources, our software picks it up, shows you the two feeders, and then you have your feeder settings. You have feeder 1 settings, and you have feeder 2 settings. So all the settings you have for each feeder are there. We'll do one more thing. Let's see if we can connect something to that. I'm going to try and take LP2B and connect it to it or something like that. Let's go back to this. Perfect. We'll take this one, and we will change it to be connected to my transfer switch. So now if we run our panel edit, so there we got LP2, transfer switch, LP2B below it. You'll notice that the transfer switch is listed here. It doesn't list the stuff below it again. It gets a little messy if you just keep doing that. So we show the things below the transfer switch on the main feeder 1. We figure feeder 1 is the normal connection. So feeder 2 is shown just so you have some sense of where it is, but the rest of the stuff is shown below the feeder 1 instance of it. Now we can take this over to the OneLine diagram. Here's LP2. There's LP3. So there's the panels that we're going to be connecting to. Run our update. It'll pull in the information that's changed. You'll notice that it disconnected this panel, so that feeder isn't there because it's actually connected to the transfer switch. It didn't move it. It just said, well, I at least know that feeder doesn't exist anymore, so let's get rid of that. I'm going to pull this one over here, and then we'll insert. I'm just going to manually insert this transfer switch, select it. I've got the transfer switch chosen. I actually want this one, so it's going up and down vertically. I will use the bigger one. Place it on the drawing, and it will put in the two feeders and then the feeder to the device below it. At this point, all our standard features work for the OneLine stuff. And that is how you do a transfer switch. So the first part, the hard part, is create a transfer switch in Revit, properly modeled and connected. Once that's done, Design Master handles it just fine. Thank you for watching today's Design Master training. Contact us with questions or comments by calling 866-516-9497 or emailing support@designmaster.biz.